Okay,
Yeah.
so for the last talk of the day, we have Barak Weiss from Tel Aviv University speaking on pushforwards of rational fractal measure. Barak.
Okay, thank you, John. So first I want to thank the organizers for the invitation. And it's unfortunate that I couldn't make it. I would have been much happier to come than spend my time here in Israel in a complicated situation. But thanks again for the invitation. Thank you for coming. I apologize again to the organizers for stressing them out during my scheduled talk on Tuesday. And thank you to Sang-Hee Lim for pinch hitting for me. So this is and please stop me as soon as you have questions. I can't see your faces, but I think I can hear you if you have questions, and please don't hesitate to stop me and ask questions. This is a joint work with Osama Khalil and Manuel Luethi, and I'll start with, it's about dynamical systems, resultant dynamical systems, which is helpful for proving a result in Diophantine approximation. So I'll start with the history of the field that I want to call Diophantine approximation on fractals. And it's a very incomplete history, but it's the history that's relevant to this lecture. And so let's let phi be an approximation function. So it takes as input natural numbers and returns positive real numbers, and it's decreasing. And a vector, we're going to be discussing Diophantine properties of vectors. A vector in RD is called phi approximable. There are infinitely many solutions. Oops, sorry. QP, where here Q is a natural number and P is a integer vector to the inequality, the norm of QX minus P is less than phi of Q. So what you should think of as you increase Q, which is you can think of it as the denominator in the approximation. So this inequality is the same as saying X minus 1 over Q times P is less than phi Q over Q. So on the on the left-hand side, you're getting an approximation to X by Q, and on the right-hand side, you're measuring the quality of the approximation, and the quality of the approximation has to improve as Q increases. So that's your standard question in Diophantine approximation, and the kind of landmark achievement in the theory of so-called metric Diophantine approximation is Khinchin's theorem, and I'll also stick in the name of Groshev here, and it gives a necessary and sufficient condition for this being satisfiable in terms of phi for almost every x. So the theorem says if the following series diverges, then almost every x satisfies this property, and if the series converges, then almost every x is not. Okay, and so the almost every in this statement right here is with respect to Lebesgue measure in Khinchin's original result. I should say Khinchin proved this in the 20s, and then Groshev extended it in the 50s to, Khinchin proved it for d equals 1, in other words, for real numbers, and then Groshev extended it to vectors and matrices in the 50s. So that's why I'm mentioning Groshev's name. Let me state a special case, something that easily follows. So special case, two special cases, in fact. Let's fix some positive epsilon and look at phi of q equals 1 over q to the power 1 plus d plus epsilon, phi approximable, if there exists, if there exists some epsilon such that x is phi approximable for this phi, then x is called very well approximable, which I'll abbreviate by VWA. And so as a corollary of Khinchin, you get that the Lebesgue measure of the very well approximable points in RD is 0. And so that's special. That's one consequence. And the second consequence is about the opposite extreme. So if there exists a positive C such that for another value of phi, so for phi of q equals C over q to the 1 over d, x is not, let me phi approximable, then x is called badly approximable, which I'll abbreviate by BA. And so the another consequence of Khinchin's theorem is that, again, that the Lebesgue measure of the badly approximable set is 0. Okay, so these are two very simple consequences. I'll just sort of very, very quickly go over this. So the threshold here is whether or not this series converges or diverges. And if you stick in this epsilon, since you're raising to the power d, the sequence converges. And so so you get the first statement that I made about VWA having measure 0 from this thing. And on the other hand, for any positive C, if you look at this function and insert it back into the formula here, you see that the series diverges. And so for every C, this is set a full measure where this is where the points are phi approximable for that phi. So the complement, which is this BA set, has measure 0. Okay, so I hope that's clear and familiar. And now I want to remind you of the dynamical interpretation of these two corollaries. So dynamical interpretation. And this is what's now being called a done correspondence. And I'll say a few words about the history here. And the correspondence is as follows. We set up a space, which I'll denote by this calligraphic XD plus 1. It's the space of lattices of covolume 1 in R to the D plus 1. So this is probably, I know that this was mentioned in Sang-hee's talk. It's probably been mentioned several times during the conference. This is the space, and on this space, we have a dynamical system given by a one-parameter diagonal flow. And I want to use the following matrices. I take diagonal matrices that have two eigenvalues. The positive eigenvalues are all equal to each other. There are d of them, and the negative eigenvalue makes the determinant equal to 1. So this lives in SLD plus 1. And I want to define a lattice as follows. One's on the diagonal. The entries of the vector on the right-hand top corner, apply this matrix to z to the d plus 1, you get a lattice in the space of lattices. And the Diophantine properties of X are encoded by the trajectory of this lattice in the space of lattices. So X that the theorem is, just let me call it a proposition, and I'll mention the names of Dani, Steinbach, and Margulis for this. But this is really, it has a history and it's not extremely difficult. And X is boundly approximable if and only if the forward trajectory of this lattice has compact closure in the space of lattices. So as you probably all know, the space of lattices is non-compact. And so if the trajectory stays bounded, that's necessary and sufficient for being boundly approximable. And X is very well approximable if and only if there exists a positive C and a sequence of times Cn going to infinity, such that the distance between the image of the initial lattice under the dynamics of time Tn and any base point, let's just call it lambda 0, increases at linear rate. Here, there's various notions of distances on these quotients G mod gamma, but there's a natural distance coming from a invariant Riemannian metric, a right invariant Riemannian metric on the group. And so you get a natural meaning to this distance function, which appears here. And so briefly, the history is that Dani wrote down the first statement, and Kleinbach and Margulis wrote down the second statement, and they have more refined statements. And they Dani's paper was in the 80s. Kleinbach and Margulis did this in the 90s, and they called this the Dani correspondence. So you're going to be seeing some more instances of this correspondence soon. And I should also mention, so this is about the two consequences of the two properties that I mentioned as consequences of Khinchin's theorem. They have a Diophantine interpretation. Remark, Kleinbach Margulis give a dynamical sufficient condition for X satisfying the conclusion of Khinchin's theorem. I'm not aware of a necessary and sufficient dynamical necessary and sufficient condition that works for all functions. I don't think it's very deep questions, but maybe it'd be nice to have something like that explicit written down. So the goal, you'll see in a moment why I mentioned this remark. The goal of the work of many people, including what I'll describe today, is to extend either the full Khinchin theorem or its consequences mentioned above to other measures in place of Lebesgue. In particular, to fractal measures. So another thing to say here is if you give me an explicit, concrete point, X, it can be quite difficult to determine whether or not it's BA or VWA or whatever, even for real numbers. I mean, nobody knows, for example, whether cubic root of 2 or pi are BA or VWA. These are kind of long-standing, very hard to reach, apparently, open questions. And so the measure theory is easier, and for general measures, it's still quite challenging. And so which measures are we going to be discussing? So examples of measures we will be discussing. The measures should have some kind of geometric properties. So in order to get started, so they're going to be fractal measures. So first, let's look at certain examples of nice fractal. And I'll say a little bit more explicitly what I mean by a nice fractal in a moment, but just to give some examples, such as Cantor's middle third set, or the Menger sponge, or the snowflake, or a bunch of other examples. Take mu to be the Hausdorff measure of dimension of the fractal restricted to the fractal. So what I'm trying to say is a certain collection of so-called nice fractals have nice measures associated with them. And those are the kinds of measures that I'd like to consider. Let's start with the Cantor set, which is probably the most familiar to everybody. So when I say Cantor set, I really mean the middle third set, not just some kind of abstract, totally disconnected perfect set, but you take the actual Cantor middle third set. On it, it has Hausdorff dimension log 2 over log 3, and there's a measure on it, which is, as you know, the Cantor middle third set can be written as all real numbers whose base 3 expansion only uses 2 digits 0 and 2. You can define a measure on it by IID choosing the 2 digits 0 and 2 at random with equal probability, and then you get a measure supported on the fractal, and this turns out to be the Hausdorff measure. Let me, since I prepared the pictures, I'll show you the two other. This here is a picture of the Menger sponge. If this is what I was told by Wikipedia, so I hope you can understand how you construct it in analogy to the Cantor set, but you work in 3 dimensions, starting with a cube and making holes in it. So it's a measure 0 set of some Hausdorff dimension strictly less than 3. And this is the snowflake. Actually, this is just, I chose this picture because it's sort of attractive, but the snowflake is what's usually called a snowflake is the fractal set you see on the boundary of this thing, which is a curve of infinite length and Hausdorff dimensions strictly between 1 and 2. So those are the 2 fractals. Each of those 2 fractals has also a nice measure on it, the Hausdorff measure in the appropriate dimension. So these are examples of the kinds of measures that I'd like to consider. And now I'd like to be more formal about defining them. So more formally, I'm defining a similarity map from RD to RD, contracting similarity map. If there are a contraction ratio C between 0 and 1 and an orthogonal transformation from RD to RD and and a vector y RD such that f of x equals C O of x plus y. So these are affine maps that preserve angles in the Euclidean sense, and they contract everything by a constant factor of C. So these are like conformal for the Euclidean metric. And so these are called contracting similarities. And for suppose we have a finite collection of them, of at least two such maps, F1 through Fk, we can get a fractal from this piece of data in a canonical way. We get a map that sends an infinite sequence of symbols to I'm writing, let's just call this map COD for coding. This is the coding map. It maps an infinite sequence I1, I2, I3. These are an infinite collection of symbols between 1 and k is being mapped to the limit as n goes to infinity of what you get by successively applying these maps to a base point and taking limits. So this is well known that this converges. The convergence is to a limit which is independent of this initial. The fact that I started at 0 is not of any importance, and it's a continuous map from the symbol space, from the symbolic space, into RD, and its image the image of this coding map, call it K, is the attractor of these collection of maps. It's the unique compact non-empty set, which has these particular maps as self-similarity. So in other words, the sets that are obtained this way are self-similar under these K contraction mappings. If now we take a probability vector, P1 to Pk probability vector, so that means that these are positive numbers that sum up to 1, then we get a Dirac, a kind of a Bernoulli measure on the symbolic space. So this is the measure that chooses the I symbol independently with probability Pi, and you do this countably many times. So this is the measure on the symbolic space, and now you push it forward by the coding map, and this thing, such a measure, has support K, and we call it a Bernoulli measure on K. Because this on the symbolic space, these are Bernoulli measures. Okay, so these are the kind of measures for which our results will apply. And this measure is distinguished in the following sense. It is, let's call it, let's denote it by mu sub k. Of course, it also depends on the choice of these PIs, and it is the unique measure. Mu satisfying a kind of stationarity property, sum I equals 1 to k, Pi times Fi star mu equals mu. So this is stationary. Okay, an important point to make right now is that the Fi's individually don't preserve this measure, but on average, they do preserve this measure, and that's this stationarity. So for appropriate choices of the PI, we get the Hausdorff measure. So these are the measures that I'd like to consider, and let me add some, appropriate choices of the PIs. You get the Hausdorff measure, assuming some separation condition that I don't want to spend time on. So in other words, the images of the Ks under these FIs should be either disjoint or almost disjoint, and that's what I call a separation condition. So these are the measures that I'd like to consider. Again, if there are questions, please do stop me. Now I'd like to show you a table which I prepared about results and when sort of a history of, this is what I'm calling this biased history. I want to talk about some results regarding the Diophantine properties of typical points with respect to these measures. And so the three papers that I'd like to highlight are my joint paper with Kleinbach and Lindenstrauss from 2004, a follow-up paper of Einsler, Fishman, and Shapiro from 2011, follow-up of myself and Simmons from 2019. In the first paper, the Diophantine result was that VWA has measure 0 under very mild conditions. So just think of these conditions. These are conditions. Just think of them as being very, very mild. But this result says nothing about the badly approximable set, its measure. And the measure of the badly approximable set was proved to be 1. This was an open problem for a while, a fairly well-known open problem, say for the middle thirds Cantor set, because it gives your measure to badly approximable points. This was settled by Einsler, Fishman, and Shapiro for dimension 1 and for measures which are invariant under multiplication by p for some p. So an example here would be the Cantor measure. So e.g. Cantor set, middle third set. But they didn't treat higher dimensional fractals, and they also did not, they actually worked with the honest Cantor set, which is truly invariant under multiplication by 3 mod 1, and not some shifted version. Then in the paper with Simmons, we removed these conditions. We got general D and much weaker conditions, and we were to prove the badly approximable set has measure 0. Underlying all of these results, there's a kind of a basic dynamical result. I'm not claiming that the implication from the dynamical result to the Diophantine result is obvious, but I just want to tell you what goes into these proofs. And so in the paper with Kleinbach and Lindenstrauss, the main point was you take a measure nu, which I guess I should define. So nu is the push forward of mu k, the measure on the fractal, the Bernoulli measure on the fractal, under x maps to lambda x. Remember, we had this mapping that sent points, vectors to lattices, vectors in Rd to lattices in dimension d+1. And so you get a natural measure from the measure on the fractal on the homogeneous space. And now if you start pushing it by the diagonal flow, where the diagonal flow is the one that appears in the Downey correspondence, then no escape of mass is what's needed for proving the first, in my paper with Kleinbach and Lindenstrauss. And to prove this, this is the technical statement. It goes under the name of non-divergence for unipotent flows. You're not seeing a unipotent flow here. I'm not even defining unipotent flow here, but this is technically what you need to know. So for every epsilon, there's a compact subset of the space such that this push measure gives all but epsilon of the mass to it for all t. Okay, moving on to this second paper of Einsler, Fishman, and Shapiro, they needed something else dynamically. So they proved that for almost every, nu is the same nu, and then the positive trajectories of lambda x are dense. I mean, they didn't, strictly speaking, they didn't need it, but they were able to prove it. And dense where? Dense in the space of lattices of 2 dimension. And in the follow-up paper with Simmons, what we were able to prove is a strengthening where in fact, these pushed forward measures, these trajectories under this diagonal flow, not only are they dense, but they're actually equidistributed, and the dimension is arbitrary. And it's interesting to know that the technique of my paper with Simmons is completely different from the technique of Einzler, Fishman, and Shapira. What gets used in the Einzler, Fishman, Shapira work is related to Lindenstrauss and Einzler, Kotok, Lindenstrauss. It's about higher rank toral actions on homogeneous spaces, and the homogeneous space in question is a kind of S-adic homogeneous space. Namely, you take quotients of groups that are algebraic over reals and over p-adic fields. And the technique with Simmons is different. We classify stationary measures for a certain random walk on this quotient. I'm not going to define the random walk for lack of time, but our technique, this BQ stands for Benoit count, and everything we did in this paper employs ideas of Benoit count. So this is I've sort of set the stage for previous works, but this was all about, maybe I'll mention one more recent breakthrough, which is due to Khalil and Luethi, who are my collaborators in this project, and I'll write that down. So Khalil and Luethi actually, as you're seeing, all the previous results were about the measure of the badly approximable set or the measure of the very well approximable set, but we didn't have a Khinchin theorem. And now we do have a Khinchin theorem in some cases. So this is theorem, beautiful work of Khalil and Luethi, and it was published last year in Invenciones. And this is what they prove. Suppose I'm making two assumptions. Fi's are rational, so all the coefficients that appear in the matrix O, in the translation vector Y, and in the contraction ratio of these similarity maps, all these numbers are rational numbers. And also a certain inequality saying that the dimension of K is large enough to satisfy. I'm not going to state it, but it's some kind of mysterious inequality involving the relationship between some spectral data. Then Khinchin's theorem holds for this measure, this fractal measure. They don't make any assumptions about the dimension, but they do have these two assumptions. Now, let me give an example. Let me give a few examples just to explain this. So example, middle thirds Cantor set satisfies A, but not B. So it's still an important open problem to prove Khinchin's theorem for the middle thirds Cantor set. That's kind of a benchmark problem in this field. This is called Mahler's question. So a shift of middle thirds set by X irrational does not satisfy. Does not even satisfy A. Middle fifth Cantor set satisfies A and B. So if you remove 1/5, the middle fifth of the Cantor set at each stage, then you get a fractal. It's got a higher dimension than the middle third set, and then you can apply their work. Okay. So this is their paper, and I want to make a couple of remarks about these conditions. So this condition is stringent, but everything hinges. You can't set up the dynamical statement that they work with, which I'll say a few words about soon. the space on which you act depends on this rationality. So this is sort of crucial. I'm going to just move a little bit so I get sorry. This condition about having large enough dimension is sort of artificial. I mean, you see this in my examples. Why on earth should your method prove a kinship theorem for the middle fifth set, but not for the middle third set? And so that's the motivation for our work. What we wanted to do was relax the second condition if possible, and we're not completely able to do that. But I'll tell you what we are able to do. But before that, let me tell you what the main dynamical input was of their work. Main dynamical ingredient of paper of Khalil and Luethi is the following. It's called effective equidistribution of pushforwards. And so it says that if you take nu is again that measure coming from the Bernoulli measure on the fractal embedded in the homogeneous space, you push it by the diagonal matrix T, and you let T tend to infinity. This tends to our measure on the space of lattices. And moreover, it tends to this effectively. So meaning that if you plug in, if you sample a smooth function of compact support on this space, then you you get a rate in this equidistribution. So they needed both the rate and the equidistribution of the pushforwards, but the equidistribution of the pushforwards was not known prior to their work, and that's a very natural dynamical question as to, do these measures equidistribute when we push them by the diagonal flow? Okay, so here is another sort of a thing that they introduced. They introduced something that I want to call KL random walk. It's a random walk on the space of lattices, but it's not exactly a space of lattices, it's a bigger space. So curly x d plus 1 with an s on top. Remember, curly s d plus 1 was a space of lattices dimension d plus 1. Now we're taking a quotient in a S-adic setup. So I'll explain these terms in a moment. So you take the group PGLD, which is an algebraic group. Instead of plugging in real numbers, you plug in real and p-adic numbers for all primes P and S. S is the set of primes appearing in the maps, the iterated function system that defines your fractal. So it's a finite set of primes, and you do this for this finite set of primes, and you get this kind of hybrid homogeneous space, which looks like a real homogeneous space with some kind of p-adic or solenoid. You can think of it as a kind of a fiber bundle over the space of lattices, where the fiber is some kind of p-adic or solenoid type space. And this is this on this space they apply certain maps, and the maps are the following maps. I just want to the random walk. So move. Oops, sorry. Move in this space by randomly choosing one of the HIs and applying it. Or what are the HIs? I'll just do the Cantor set case because it's simpler. In general, it's sort of a similar thing. In the Cantor set case, there are two maps, and the HIs are the following: 1/3, 0, 0, 1. 1/3, 0, 0, 1. That's one map. The way here we have S equals 3. So this and D equals 1. So these spaces that you're seeing on your screen, on the screen, these matrices are 2x2 matrices with a real and 3-adic component. And so this is the real component, and this is the adic component when I write things down in this way. And the second matrix has the same real component. The adic component is some other number with a 3 in the denominator. Has to do with the translation vector of the IFS. And so you're pushing, so these matrices act on this, act on this space, and you're pushing them around to, you're pushing points around by choosing them randomly, IID, and moving things around. So that's the random walk that they introduced, and this played a role in their proof. And in our recent work, let me just check. So I have, is that true? I have 10 more minutes? Complete silence. So I can't hear you, but I'll assume I have 10 more minutes. So actually, this is disturbing.
Barak, you've got 20 minutes.
I have 20 minutes.
Full hour.
Okay.
Yeah.
I'm doubly relieved, both that I have 20 minutes and that someone is actually listening. So, yeah, good. So let me not rush too much. So I have these two maps. I apply them in the homogeneous space, in this S-adic homogeneous space, and push points around. And this is the Khalil Luethi random walk. And I'm going to ask two questions which turn out to be closely related. So, and these are the questions that we're trying to address in the new work. Questions. One, can we prove equidistribution of these measures as t goes to infinity in, let me emphasize here that what space we're in without assuming the rationale, the inequality B that I mentioned before. So again, this is a question that I stated without writing it down. I'm just reminding you what Khalil and Luethi proved is if you have two conditions A and B, one of which I find somewhat artificial, if those two conditions hold, then as t goes to infinity, this measure tends to the Haar measure, and on top of that, you get an effectivization, you get a rate in the equidistribution. Now, I'm willing to. This is kind of weird in ergodic theory to obtain a quantitative result and a quantitative result at the same time, namely an equidistribution and a rate, without having another proof which is easier and has no rate. So question one is, can we get the qualitative statement? Can we get an equidistribution statement without a rate, perhaps, under weaker conditions? And the second question, which might not appear related to, but it's very close, what are the stationary measures for this Khalil Luethi random walk? Let me remind you, mu on this bigger space is stationary if when you push it by the random walk elements, weighted by your Bernoulli weights, an average, you get back mu. So this is a kind of stationary measures are sort of the natural objects of study if you're studying random walks, because they sort of survive, they're stable under applying the random walk. Typically, I mean, obviously, if mu is invariant under all the maps in question, then it's stationary. And typically in probability theory, there are going to be stationary measures which are not invariant for the group elements. And there are existence results saying that stationary measures always exist, but invariant measures might not. And the results of Benoit and Kant that I mentioned earlier are kind of striking rigidity results for homogeneous dynamics. And they show that, in fact, all the stationary measures are actually invariant under all the elements of the acting group. So this is kind of a background on why we care about stationary measures and what they are. And it turns out that question 1 and question 2 are related, even though it might not be clear to you at the moment. And notice that the measures and the questions are about different spaces, actually. Okay, so this is the these are the questions that we'd like to address. And now let me tell you the answers that we have. This is a work in progress. There are still many things we'd like to do and improve, but we have some partial results at least. So the first theorem is so suppose all the FIs are rational maps without rotations. So these are contracting similarities that do not change angles at all. And S, the set of primes that appears in the denominators, is just one prime. There's just one prime in the denominator, and we're going to call it P. So single prime, no rotations. Then we get the result that I asked about. Let me make a comment about these two assumptions, that no rotations and single prime. So, and I'll do that by showing those two pictures again that I showed earlier. So remember we have this sponge and we have this snowflake. Now, for the sponge, all the contractions are, so here P is 3. There's just one contraction in the similarities. There are no rotations. Essentially, the entire sponge is mapped into kind of a piece. I'm just highlighting one of them here. So each of the similarities maps this entire sponge by contraction and a translation exactly into one of, I don't know exactly how many, 8 plus 8 plus 4, I guess 20 of the 27 possible subcubes of 1/3 the size. So those are your maps. And there are no rotations, and they all contract by a factor of 3. And 3, if you write it out, it's prime decomposition, you just end up with 1 prime. So this satisfies our conditions, as does the middle thirds Cantor set. This guy here, the snowflake, does not. So actually for the snowflake, what you get is you see that, say, this entire piece here is identical up to a rotation and a contraction to this piece. And so you do get you have to rotate by 60 degrees to see the contraction. So the contractions here are by a factor of 1/3 still for the snowflake, but there are rotations involved. So our theorem does not apply to the snowflake, but it does apply to the sponge. Okay, I hope that clarified the conditions. So this is theorem 1. And let's call this theorem 1. And theorem 2 is supposed to be an answer to question 2. So same assumptions, in other words, no rotations in 1 prime. So let nu be an ergodic stationary measure on this hybrid space for the Khalil-Luethi random walk, then one of the following mu could be invariant, which is one obvious measure that we know of, which is stationary. It could be the Haar measure on the entire space. Or something else might happen, and this is what we can prove. There is X such that nu gives full measure to a certain orbit of a certain group of X under a certain group H minus. H minus is I'll just write it out. It's a group that looks like this. A group of matrices that are identity in the p-adic place and are upper triangular in the right-hand column in the real place. This is case 2. And case 3 is the state there exists X. So that, so let's say for almost every X, sorry. For almost every X. With respect to the measure nu, or nu, almost every X, the stabilizer of X intersect L is not the identity, where L is yet another group, and it's a real group, PGL D plus 1R, sorry. The entire real group cross kind of a similar group in the p-adic place that I was thinking that I had before. Okay, I just wanted to have a explicit, precise theorem 2 here for you to stare at. But let me sort of zoom out so you can see the entire theorem. Let me say a few words about what we would really have loved to prove. We would have loved to give you a list of all the stationary measures for this random walk. And that's, as I said, this is a work in progress, and I'm hoping that eventually we will be able to do that. Unfortunately, we cannot, but we give you a kind of a set of conditions that a stationary measure must satisfy if it's not equal to the Haar measure on the entire space. And there are additional stationary measures, as you'll see in a second, come up in this setup. So the list it can't be that these 2 conditions can be completely removed, but if we're lucky, we might be able to say, well, in case 2, here's the list of possible measures. In case 3, here's the list of possible measures, and so on. So these are our results, and let me state a Diophantine corollary, and then just say very briefly a few words about proofs. So a Diophantine corollary of our paper is something that also has attracted attention. This is only interesting in higher dimensions. Suppose this is called the weighted Diophantine approximation. So here, suppose you have another set of numbers that add up to 1. You could think of it as a probability vector, but it's traditionally called the weights. So R1 through RD are weights. Sorry, R1 through RD are the so-called weights in a weighted Diophantine problem. That means that all the Ri are positive, and sum up to 1. I'm going to make another definition, Diophantine definition. So X, a vector is called R badly approximal, where R is this collection of weights. If there exists a positive C such that for all Q in C, D, Q in N, there's a condition. This is some kind of Diophantine inequality. The point about calling these weights is that if the Ri's are not all equal to each other, then different coordinates get different exponents. Here, you can check easily that if all the weights are equal to each other, namely they're all equal to 1 over D, then this coincides with the classical definition. But for new weights, other weights, this is a different Diophantine condition, which has also been studied. And this, there's an, as I said, there's an extension of Dani's correspondence to the weighted setup. As I didn't say it, but I hinted at it. And here's the statement. This property holds if and only if the trajectory of the same lattice under a different group has complex closure. So I'm changing this group that's acting to a new diagonal group. The diagonal group is instead of having equal positive eigenvalues, I make my eigenvalues depend on the weights. So this is classical. This Dani correspondence for this weighted setup is due to Kleinbach. It's been around for a very long time, and so you can also profitably study this notion through homogeneous dynamics. And up to our work, it was not known what is the whether this is a set of measures 0 in a fractal. It was known that this is a set of measures 0 in the space. That's not easy to prove using this correspondence. But in the on the fractal, we get the following. Let mu be as in theorems 1 and 2. So sorry, not mu, that the contraction mapping speed is in theorem 1 and 2. Let K be the attractor, and let mu be a Bernoulli measure. On K, then mu almost every X. Let R be a weight. Weights. Then mu almost every X in K is not badly approximal for these weights. So this is the Diophantine corollary. Let me very briefly tell you just a tiny bit about the proofs, ideas involved. Proofs of theorems 1 and 2. So for theorem 2, which is our main theorem, it's the one about the stationary measures combined. Let me not say much. I'll just say we combine ideas of the paper BQ that I mentioned, Benoit and Kant, my paper with Simmons. I don't want to say more about it. We sort of try to find the weakest possible hypotheses under which the arguments of those papers can be pushed through. And when these hypotheses hold, we can get this conclusion. We arrive at this kind of a conclusion. But there are other cases where we can't run the arguments, and they sort of lead to these two cases. That's a very, very rough outline of sort of what's going on. And let me say how we get theorem 1 and also how we get this corollary from theorem 2 very, very briefly. So what you do is, remember there are two spaces. So there's this space of lattices, which I denoted by xd plus 1, and then there's this S-adic space covering it. And as I told you, the fiber is this kind of a p-adic solenoid on top. And we had nu here, and we can form a nu bar covering it under this map. Nu was the image of the measure on the fractal under the map. X maps to lambda x. Here we define x maps to something quite similar. Sorry. The lattice, remember, is I'm going to denote by gamma s. So you look at the coset of this element. So in other words, in the definition of x, the p-adic component is trivial, and that's a way of lifting the measure nu to a measure nu bar upstairs. And if we can prove that we let AT also act upstairs, by acting only on the first coordinate, namely it's acting trivially in the p-adic places. And the advantage of this now is that mu itself, the image of mu k under this map, the map that I see here, is stationary for the Khalil Luethi random walk. So you always get at least one more stationary measure. The random walk commutes with the diagonal flow. So all accumulation points of this trajectory so this is nu bar. All the accumulation points of AT nu bar are also stationary. And your goal becomes showing that the only possible accumulation points are the ones, are the Haar measure. And to do that, you have to rule out accumulation points of these two types. And to do that, you play a game which is sometimes called something akin to the Dani-Margulis linearization technique, to show that these push forwards cannot give, in the limit, positive mass to orbits of this type or to points which have stabilizers of this type. So that's a very rough sketch, and I thank you for your attention. Happy to have a